Yeah, hello. Hi, everybody. I hope you hear me well.
Yeah, sure.
Okay. Okay, so thank you for the invitation. I'm very happy to be with you and share my knowledge, or let's say poor knowledge, of asteroids. So what I want to do in this talk basically is to show you what we learned so far with recent space missions and the problems that we encounter when we try to explore asteroids and interact with them, and what we can learn about it for asteroid mining. And actually, the previous talk, which was on granular material, is highly relevant. The only issue is that we don't really know before we go to see an asteroid what are the properties of this material, and in addition, how it behaves in its gravitational environment. So first, I want to recall why we study asteroids. So asteroids are really fascinating because there are many reasons to study them. Of course, there is a scientific reason because we think they are among the best tracers of the formation and history of our solar system, because they record the original composition of the solar nebula in which the planet formed. Then there is also a reason related to the impact risk. And then there are reasons related to resources, and this is the aim of this meeting. And in fact, all these reasons essentially require the same knowledge. We need to understand their compositional properties and also their physical properties, and in particular, how they respond to an internal action like a tool that wants to basically exploit them. And so whatever the primary goal of a mission, whether it is because you want to do science or planetary defense or mine the asteroids, the knowledge you get will feed these three very different communities, which I think is very exciting. So recently we had two fascinating missions which got samples of asteroids. So the OSIRIS-REx mission by NASA and the Hayabusa 2 mission by JAXA. And in particular, Hayabusa 2 returned already the samples on Earth, and they are currently analyzed in the lab. So I will start with Hayabusa 2, then OSIRIS-REx, and we'll go to the next missions, at least two of them, showing you basically what we found and the surprises we got that will make us best prepared for interacting with them in the future. So Hayabusa 2 was a success story essentially because there was a series of very complex operations and all were extremely successful, which is really exciting, starting from the launch, of course, in 2014, and then the arrival at the asteroid and the deployment on several surface packages, in situ measurements, two samplings, and an impact experiment, and eventually a successful return to Earth on December 6, 2022. And essentially what we found is that the body, which was the target of Hayabusa 2, Ryugu, is a very dark object. And the first thing you do when you arrive at the asteroid is try to understand what you see, basically, because what you see is so far very different from what we thought from the Earth. And therefore, you need to make a shape measurement, also measure the gravity field so that you can better operate around the body. And in the case of Hayabusa 2, they didn't go into orbit, they did hovering. So they stayed at 20 kilometers from the asteroid and sometime getting down. And then you start to basically understand the global properties and also the composition, as you can see with the near-infrared spectra, which resembles some of the primitive meteorite that we have on Earth. And that way you can possibly better operate and be in better position to choose the sampling sites or when you want to mine basically the asteroid. Of course, the problem for mining, but it's a very exciting point for scientists, is that these bodies turn out to be very, very complex geologically. They have a variety of geological features, as you can see here for Ryugu, where we have a trough, we have a bulge at the equator, we have a lot of craters and boulders everywhere. And these boulders also have very different morphologies, one respect to the other. So that's something that we didn't really expect when we arrived there. And that poses problems when you want to land, because your landing accuracy has to match basically the constraints given by the amount and distribution of boulders. And so the first sampling took place in February 2029, and as you know, it was a touch and go scenario where basically when the sample arm touches the surface, a projectile of 5 grams is launched at 300 meters per second, and when it impacts the soil, then some grains, we hope, go into this horn and then are captured into the re-entry capsule. And the aim was to get 100 milligrams of samples. And in fact, the problem we had, and it would be too long to explain that during this talk, is that the landing accuracy originally was about 50 meters. And when we arrived at the asteroid, we saw that actually we don't find any places where we can land safely, which is larger than a few meters. So the Japanese operation team had to revise entirely their strategy of landing in order to increase their landing accuracy, which is not super simple when you are there. So you have to anticipate these kind of things before you launch your missions and have a sort of flexibility in your approach so that you can easily switch from one approach to the other depending on the context. The simplest context, obviously, you can use the simple approach, but if you're already prepared for a more complex approach, that's even better. Unfortunately, the Japanese could do some rehearsals, sacrificed one sampling for that, and the sampling was extremely successful. They landed at a 1 meter accuracy with respect to the center of the landing site. And this is a movie showing you the sample arm touching and then all the ejecta that were released by the impact. And there were so many ejecta inside, outside the horn that we hoped there were many ejecta inside. Actually, we did some simulation of this. Oops, sorry, it doesn't go well, but you can see the sample horn and the ejecta field. And what you see outside, actually inside this simulation, we got 1 gram of samples. So we're quite optimistic that we got good samples. And effectively, there were 5.44 grams collected during the 2 samplings, which is absolutely fantastic, 54 times more than we hoped. So with that, of course, you can do a lot of science, and that's very nice. And soon there will be some results that will be published. Then there was another exciting experiment, which was an hypervelocity impact. So basically, there was a bug that was released from a spacecraft at 100-meter altitude. And when it exploded, it gave a kinetic energy to a projectile of 2 kilograms, launched at 2 kilometers per second. So the aim was to reveal the subsurface composition, but also to check our understanding of impact physics in a low gravity. And in fact, you can see here the movie taken by a small camera called DKM3 of the impact itself. And surprisingly, we saw a lot of ejecta falling back on the surface. And that was surprising because an impact at 2 kilometers per second, you expect the ejecta going away at velocities much larger than the escape speed of Ryugu, which is only 20 centimeters per second. However, we saw a lot of ejecta falling back. So that showed us that, okay, these bodies have a very strange behaviors against all the processes they experience. And the impact physics, we have to think about why we cannot capture that in the modeling, because the modeling was predicting that the crater would be large, about a few meters in size. And you can see here before the impact and after the impact, the crater is about 15 to 17 meters in size. And the only way to explain this large size is if you remove the cohesion and the strength from the equations, basically. So basically, this surface behaves like a cohesionless surface, which is kind of surprising because before the impact, you see a lot of boulders, which normally you expect there is strength because you have a solid rock. And in fact, these rocks appear solid, but in fact, they are very weak. So the bottom line is, if you really want to understand the surface properties, you cannot necessarily rely on the images because you need to touch. These boulders could be solid, but effectively, when you touch, they may not be solid at all. So that's one of the complexities that until you touch really the surface, it's very hard to predict what will be the reaction. So fortunately, with these kind of missions, we learn little by little these kind of things, which will be super helpful for mining. Another thing which is important also is, of course, the color as it changes, the spectral color with the exposure to the solar radiations and micrometeorite bombardments. And what you can see here, I mean, you don't see on the image, but basically the surface is bluer than before at the bottom of the crater, which means that younger means bluer. Because when you make an impact, you reveal newly exposed material to the sun. And this newly exposed material will tell you how the fresh material looks like. And on a Ryugu, the red material is basically older than the blue material. So for mining, if you are more interested in fresh material, you know what kind of color you have to look for. Then there was another mission, OSIRIS-REx, which also went to another carbonaceous asteroid. This time, the spacecraft went into orbit, which was also really exciting. And doing so, we have a full coverage of the surface with high detail, plus the camera was absolutely excellent. And we detected some some particles ejecting naturally from the surface. So the big surprise was Bennu is an active asteroid. So you can see here the orbit of the ejecta. Some of them come back. Fortunately, they don't carry much kinetic energy, so there was not real threat to the spacecraft. But again, when you approach an asteroid and you want to mine it, you have to be careful about this kind of thing that may happen and that may not be detected before you get there. Another thing, as you can see here, and that was the same for Ryugu, but here you have fantastic images, are the amount of small boulders and different morphologies that you can see on these bodies, like very rough, very porous and dark boulders, and more apparently strengthful with angular boulders and brighter. So that's something we are still not really understanding very well what it means, but effectively these bodies appear much more heterogeneous than we thought from the ground, and which could be actually a good news for mining, because you may find very different things even on one asteroid. And the sampling took place on 20th of October 2020. This time it was again a touch and go approach, but with a cylinder that when it touched the surface released nitrogen gas, and which floodized basically the regolith. And the hope was to get 60 grams of samples. And in fact, it was so successful that we estimate that we had a few hundred grams of samples. And the very, very interesting thing is that, again, the surface behaved like a cohesionless surface. There was basically no resistance felt by the sampling tool when it touched the surface. And again, before the sampling, the surface looked like, solid. You have a lot of boulders, etc. So again, these bodies, at least the dark ones, seem to behave like a cohesionless bodies. Whether it is true for the whole surface or not, we don't know, because we only have one experiment. But already we can see that there is a difference between what we thought before and afterwards, thanks to actual touching of the surface. And more complex is that in this case, although this is the same type of asteroids, the surface is redder after than before. So in the case of Bennu, red material is younger than blue material, which is the opposite of the case of Ryugu. So I don't know what you can conclude about that, whether you can trust spectral colors to estimate where the fresh material is. There is a way. If you have a way to discriminate between young and old craters from remote sensing cameras, then of course you can better feel what is the older material in terms of color. And that's basically what they did with Hayabusa or OSIRIS-REx. Even before these interaction, there was already a prediction that it would be that way. So it's still hope. You can be still hopeful to get something from just orbiting in terms at least on composition and freshness of the surface. So all this complex geophysics relates to basically what asteroids are made of and their history. And we know that collisions played a key role in their evolution, and most of the small ones are of at least second generation. They are fragments of larger bodies that were disrupted in the asteroid belt between Mars and Jupiter. And for the nearest objects, some resonances put them in an eccentric orbit, allowing them to get close to the Earth. So we already have a sort of knowledge of how these bodies evolve in the main belt, the fact that they are collisional products, and how they are transported to the Earth, which is interesting because that allows us to make prediction about their structure, which again relates to how you will interact with them. And what we found effectively is that when an asteroid parent body is disrupted, basically the fragments that are generated tend to reaccumulate and to form a gravitational aggregate. And this is shown here in two movies where we simulated the disruption of large bodies, several kilometers in size. And typically, you always, in the impact energy regime of the main belt, you always disrupt them in very small fragments, which are less than 100 meters in size, and they are represented there with these green dots or different color dots in these two movies. But what you can see, when the fragments go away, they tend to be ejected at the same kind of ejection speed, and therefore the relative speeds are small enough that they can feel their mutual attraction and come back together and form aggregates. And this is just centered on the larger aggregate on the movie. But if I make a zoom out, you would see a lot of aggregates forming. So basically, the outcome of a large disruption is a distribution of rubble piles. And depending on the velocity field, you will form more or less elongated rubble piles. Here on the right side, you have a rubble pile looking like Itokawa. On the left side, you will see a rubble pile looking more like Ryugu and Bennu, more like a top-shaped body. And the colors here are just the temperature experienced by the material during the impact, which is always small enough that even if you start with a hydrated body, which is something you are interested in, the fragments can still keep their level of hydration because there is not much heat experienced during the impact, which is also a good news. And you can see here the different kind of bodies that we form. And then there is another effect called the Yorp effect that also alters the physical properties of these objects. So this is an effect that can spin up or spin down an asteroid due to thermal effect. And the modeling of this spin-up effect showed that the outcome is very depending on the internal properties of the starting rubble pile. And we did some simulation showing what happens depending on the properties. And you can see on the right, the top view, on the left, the side view of a simulation where we do a spin-up. And you can see in this case that the particles from the pole, they migrate to the equator when the centrifugal force is maximum. And when the centrifugal force exceeds the gravity, they tend to reaccumulate and form a small satellite. And the way this mass shedding occurs gives this top shape, which is very specific to primary bodies of binary asteroids. Not necessarily specific because Bennu and Ryugu are also top shapes, but they don't have a secondary. So maybe they were formed differently, maybe just by reaccumulation during the disruption of the parent body. So this is interesting because that already showed that different internal structures can lead to different evolutions. But in this case, you could see that the pole is basically fresher than the equator. So again, for mining, if you understand better the physical evolution of these bodies, you can choose in a better way where you want to mine depending on what you are interested in. So the bottom line is that the asteroids are fascinating because they show us an incredible diversity between different objects, of course, with Eros, for instance, very different from Bennu and Ryugu or Itokawa, but also even on a single asteroid, you have a lot of different geophysical properties and features like landslides, gravels, boulders, you have ejecta, ponds. So you have to take care about all these in order to really understand how you will approach these bodies in order to land and do some mining, because it's not as simple as a smooth surface everywhere. But fortunately, again, thanks to these space missions, we start to have a better understanding on this that will help for future mining purposes. And then I will end with the IDA international collaboration that support these two missions, DART and HERA, that will perform the first asteroid deflection test. And what you can see here is that the DART mission was launched very successfully in November and will make an impact on the small moon called Dimorphos of the binary asteroid Didymos on the 26th of September 2022, so this year, at 6 kilometers per second. And before that, it will release an Italian CubeSat that will show us the first instant after the impact. And then the HERA mission by ESA will come on the scene, on the crime scene, as we say, as a detective to fully characterize the impact outcome and then to also characterize the whole object. So the launch, as I said, was done, and the impact is in 26th of September 2022. And the aim is to basically change the orbital period of the secondary around the primary by minimum 73 seconds, and it is about 12 hours. And then ERA will come in order to really characterize everything, starting with a launch in 2024 and close proximity operation for 6 months to really understand what happened and also have a better sense of the composition and the geophysical properties of the asteroids. So we have several instruments on this mission with cameras, of course, a LiDAR, a thermal infrared imager provided by Japanese JAXA, an hyperspectral imager, and 2 CubeSats, one in particular devoted to the internal structure of the asteroid with a low frequency radar. This has never been done so far. So we'll have a direct measurement of the internal structure, and another one devoted to the mineralogy. And also you have radio science and inter-satellite link in order to have a better understanding of the gravity field of the objects. There will be a lot of firsts because that will be the first rendezvous mission to a binary asteroid. The Janus mission by NASA in the SAMPLIX program will make flybys of 2 binaries before. And then we'll have a full characterization of Dimorphos, which is so far the smallest asteroid we would visit, which is comparable to Hotoime Saxum, which is a small boulder, the biggest boulder on Ryugu. And then we'll have the first radar sounding, and of course, a full knowledge of an impact experiment at the scale of a 160-meter asteroid. And this is important for mining because not only we want to validate the impact models at a large scale and this impact energy regime, but also Hera will give us information on the fresh subsurface composition inside a big crater provided by that. So Didymos is a S-type asteroid, so silicate type, but it will be interesting to see whether the fresh material inside the crater show us something a little different or exactly the same at the surface. And then in the context of Vanuatu and Osiris-Rex, we'll go down in the gravity level. As I said, these low gravity are very counterintuitive in the behavior of the material. So we need to better understand how some processes scale with gravity down to the low gravity of Dimorphos. And that will be possible with Hera because we'll have an understanding of the response of such a low gravity body to a hypervelocity impact. And that has a long, many implications for surface history, planetary defense, and of course for mining. Also, Dimorphos, we don't really know in which regime it is, whether it is dominated by gravity or cohesion, and that relates to its spin period. So this is a spin rate of asteroids versus diameter, and we can easily identify 2 regimes. At the large size, there is no way basically to fight against the centrifugal force with respect to the gravity of the bodies. So basically, these bodies are dominated by their gravity. And as long as the centrifugal force exceeds the gravity, they break. And that's why you don't have anybody above this, what we call spin barrier. Then at a very small size hand, since cohesion starts to be existent, then they can rotate faster. But Didymos is in this size range, which have the transition between those 2 sizes. So basically, we cannot rely on this information to infer what can be its regime of behavior, whether it is dominated by the gravity or by strength. So that's a good thing that we'll have an understanding of that with DART and Hera. I will maybe pass to that. I just want to show that the bulk density of Didymos put him in a regime where, because of the spin period, which is 2.26 hours, it needs cohesion to exist as it is. Because as you can see, depending on the internal structure, which is given by the packing of the boulder that constitutes it, you need a much larger density to make it exist without cohesion. Now, what is the level of cohesion it needs is not so big. Some simulation work done by Yun Zhang, and you can see that depending on the packing, it may evolve very differently under spin up, for instance, as you can see here. And what we find that a few Pascal of cohesion makes a huge difference in the low gravity environments. And in fact, even at the level of 0.1 Pascal, you can have a very different behavior. And 1 Pascal is just a leaf on my hand, so it's nothing. But in the low gravity, it makes a difference. So that's why I was saying it's very difficult to infer what will be the reaction of the material when you interact with it to mine it, because it's very sensitive to the local cohesion that you cannot really infer until you touch it. So maybe you have to first make something in order to understand how it works, in order to then approach correctly and do your mining operations. So with Hera, we'll have also a landing on a CubeSat, and that will also tell us, with the bouncing properties given by accelerometers, how the surface behaves with a soft landing. So we'll have different experiments on the surface. And as I always say, a direct interaction with the surface is the only way to determine its often counterintuitive response. So until with these missions anyway, we'll have a better understanding because we have different ways to touch the surface that will tell us a lot. So the bottom line, I would say, is that asteroids are really fascinating for scientists, of course, because they are more complex than we expected. And the images don't tell us all. So we really need to interact with them directly to know asteroid response to mining tools, for instance. We already found with Bennu and Ryugu that the surface of dark-type small asteroids seem to react like a cohesionless medium. Whether it is true for the whole surface or not, unfortunately, we don't know, but we have good arguments to think it's the case. And then also that low gravity bodies are very sensitive to the cohesion at very low level. So we'll have other missions giving us new information about how they behave in very low gravity. I mentioned DART and ERA. I also know there is a Chinese mission that should go and take a sample. And again, we'll learn a lot with that, and possibly, I hope, other missions. And with that, you'll be more confident that mining will not only be possible, but done successfully, I hope. And with it, I thank you very much.